I've mentioned before a neat fact about water, that H2O is able to behave as both an acid and a base. This was shown in our generalized acid and base equilibria drawn here. So what's really cool about this though, is that water can also act as both an acid and a base with itself. This property is called autoionization because water ionizes itself. And this is written as two water molecules forming one hydronium and one hydroxide. And thus the equilibrium constant for this reaction, which I write here is Kw, is equal to the concentration of H3O plus times the concentration of OH minus. Because again, we never include solid or liquid phases in equilibrium constant expressions. At standard temperature and pressure, aka 25 degrees Celsius and 1 atmosphere, Kw is equal to 1 times 10 to the minus 14. So both concentrations of H3O plus and OH minus are very small. This idea can be a little confusing because what's implied here is that pure water actually has small amounts of hydronium and hydroxide in it at all times, distinct traits of Arrhenius acids and bases. Yet we also know that pure water is neutral. So that tells me that those very small amounts of H3O plus and OH minus are equivalent, so they can counteract each other. So knowing these things, we can come to the conclusion that in pure water, the concentration of both H3O plus and OH minus are the square root of Kw, or equal to 1 times 10 to the minus 7 molar. Even in impure water, like acidic or basic aqueous solutions, this fact holds that the product of the concentrations of hydronium and hydroxide equals Kw, or 1 times 10 to the minus 14. You're likely familiar, at least generally, with the pH scale. At standard temperature and pressure, acids have a pH below 7, bases higher than 7, and water is at a perfect 7. This is because pH is a measure of hydronium concentration, where pH is equal to negative log of the concentration of H3O plus. Side note here, a couple of the most common misconceptions I see in students' understanding of the pH scale are: 1, people think of it as a measure of acidity, and sometimes then that leads to thinking that a higher pH equals more acidic. So just try to avoid that, right? As I said before, a lower pH is that of an acid, and a higher pH is that of a base. Another common misunderstanding is the belief that the pH scale ranges from 0 to 14. I'm really not sure where that comes from, but it's very much untrue, and pH can range far beyond those bounds, as you'll likely see in a few examples. So that's not all there is to know about water and Kw though. Looking back on the autoionization equilibrium, we can see that this is actually a valuable tool for understanding the relationship between acids and bases. For instance, let's also look at the generalized acid and base equilibria again. But let's pretend here that A minus and B are the same substance. Notice anything interesting about these three equilibria? Well, how about I add the acid and base equilibrium together, and then I'm going to cancel out the redundant chemicals, like the HAs and the A minuses. And voila, we have the water equilibrium again. Drawing back to chapter 14.4, that means then that Kw is equal to Ka times Kb for an acid and its conjugate base. Think about what this implies. Because Kw is constant, an acid with a larger Ka must have a conjugate base with a smaller Kb. That means then that a stronger acid will have a weaker corresponding conjugate base. Likewise, a stronger base will have a weaker conjugate acid. Let's test out our knowledge of all that we've just talked about. Say I want to compare some binary acids and their conjugate bases. Recall the acid strength trends we learned about in chapter 15.2. We can sort some binary acids from weakest to strongest, drawn here. right? HF is weaker than HCl, is weaker than HBr, is weaker than HI. Now we can define their conjugate bases, which is just the acid with one less hydrogen, and we can sort these using the principle from above, right? A stronger acid will have a weaker conjugate base. So as drawn, these bases are now going from strongest to weakest. All right, so say I have 1 molar solutions of sodium fluoride, sodium chloride, sodium bromide, and sodium iodide written here. And these are all highly soluble. So essentially, these are 1 molar of sodium plus and 1 molar of the halide counterions. Now, which of these solutions has the lowest concentration of hydronium? We can rationalize through this one by recalling that the pure water that these salts were dissolved in had some H3O plus and OH minus in it to begin with, and that the strongest base will want very badly to take the protons from existing H3O plus or H2O. So the strongest base will result in the lowest amount of H3O plus left, which is F minus from the NaF solution. Finally, which of these has the lowest pH? Remember, pH is inversely proportional to the concentration of hydronium. So the lowest pH corresponds to the highest H3O plus concentration. Just like how we talked through the last question, we can determine then that the solution with the highest concentration of H3O plus and the lowest pH is NaI. In sum, we've shown the important role of water in Arrhenius acid-base chemistry. That includes how the property of autoionization makes water more than just H2O, and how it translates to pH, and KW's relationship to acid and conjugate base strength.